Next we talk about magnetic properties in the block. On applying magnetic field to substance, either the substance is attracted by the magnetic field or it is repelled by the magnetic field. So on that basis we can classify the elements. First, the substances that are repelled by the magnetic field called diamagnetic substances like antimony, bismuth, copper, gold, silver, quartz, mercury, alcohol. They are a classification of diamagnetic substances. Usually there we see these having a paired electrons. It means their orbitals are fully filled, although exceptions can be there, but most of the time these substances have paired electrons. So what happens when we apply a magnetic field to a, here we are having a sample of diamagnetic material. When we pass magnetic field, what happens? Magnetic field lines will not be able to pass through that material and they will pass aside, not through the material. Now let's take another example. Paramagnetic substances are those which are attracted by magnetic field, like aluminium, chromium, alkaline earth metals, platinum, oxygen. They are paramagnetic materials. In paramagnetic materials, we are having unpaired electrons. Usually, unpaired electrons, greater the number of unpaired electrons, stronger will be the paramagnetic character of any substance. Now, when we apply a magnetic field to the paramagnetic substances, what happens? It will pass through it, or we can say funnel through it. You see here, what you see here? Here is line, magnetic line. It bends to pass through a material, and after going through a material on the edge, it again try to achieve its original position. So this is an example of paramagnetic materials. We just talked about paramagnetism arises because of unpaired electrons of a substance. Each electron have its spin as well as a orbital magnetic moment, and because of these, here is a electron revolving in orbital as well as rotating on its own axis. For the compound of the first transition series, 3D series we are talking about, the contribution of the orbital angular momentum is effectively quenched. We'll not go in details, but that much is good enough to remember that in 3D series, the orbital rotation of electrons will not contribute effectively for its magnetic properties. Only contribution comes from its spin on its axis. That's why that's called a spin magnetic contribution is only important for an electron, and it's calculated using a formula mu is equal to under root n into n plus 2, where n is number of unpaired electrons present for a particular element. Like for chromium, it is 6. So we substitute here 6. 6 into 6 plus 2, 48. And for any of its compounds, let's say Cr3 positive, it having a 3 unpaired electron, it will be 3 into 3 plus 2. So 15, under root 15. That will be the magnetic moment in terms of Bohr magneton, which is a unit on atomic scale, and its value will be 9.27 10 to minus 27 ampere per meter square. That was the unit for Bohr magneton. Here is another class of elements known as ferromagnetic substances. What are these? Substances which are very strongly attracted by magnetic field, like similar to the paramagnetic substances, but intensity of these magnetic lines passing through these materials is very high compared to paramagnetic materials. They are attracted much strongly than paramagnetic materials. These are called ferromagnetic materials. Like we having iron, it is a ferromagnetic material. Why transition elements are colored? The reason is when an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in visible range. The color observed is complementary to the color absorbed from a light. So here is the example of octahedral crystal field. Here we have an electron in T2G level and may be excited to EG level in octahedral compounds or octahedral complexes. So basically we can say color in the transition complexes is due to the DD transitions, which is transfer of electrons from its ground state, that is T2G level, to the excited state or upper energy level. That's what is the excess energy. These are T2G orbitals in ground state. This electron, on absorbing energy, goes to the higher energy state and giving us, and this electron will, now we have particular portion of that visible light is absorbed, but rest of the spectrum is transmitted. So transmitted light have a deficiency of particular color which is absorbed, and color we observe will be complementary to the color absorbed. That's why if the compound absorbs red color, we will see it like a violet. The other end of the spectrum, if it absorbs violet, it will looks us to red. What the other reason for the color of transition elements? Because many elements in transition, let's say scandium 3 positive, titanium tetrachloride, we see these elements don't have an electron to go to higher excitation state. So how can we have a color for these compounds? The color can be explained, or we can say for our potassium permanganate, which having a 7+ oxidation state, mean all electrons are already used, manganese. So how they can have a color for these compounds? The reason is, in such a cases we having a phenomenon known as charge transfer. What happens? In these cases, these electrons or charge is transferred from ligand to metal or metal to ligand. Because of this phenomena, we will get the similar sort of transitions we saw in octahedral complexes. So because of this charge transfer, we get in the color. So manganese, potassium permanganate color is because of charge transfer spectra phenomena. Another important property of D block elements is its catalytic behavior. Looking at D blocks, the catalysts in today's world have changed completely the face of chemical synthesis. Whatever compounds we are using in modern day life, medicines we are using on commercial scale, They are produced on scales of tons because of only these catalysts, or we can say D block elements or F block elements. Without them, we can't even think to produce those essential drugs, medicines, compounds on a huge commercial scale. So this is a very important role of D block elements as a catalyst. Now, why these D block elements act as a catalyst? What makes these catalysts so remarkable? The thing is, D and F elements, solid surfaces, have the ability to make temporal bond between the reactant molecules and the atoms of the surface of catalyst. Here we have in the surface of a catalyst, these molecules or reactants will temporarily make a bond with the reactant surface. Why D block elements will make these temporary bonds? Because they are having D orbitals. Empty orbitals are available for acceptance of electrons. Unpaired electrons are available for making temporary bonds. Or other words, we can say they interact with the surface to make it temporary transitions. The transition of metal ions, because of these change their oxidation states, or we can say they use temporarily these unpaired electrons for making bonds, and that's the only reason they are so effective to transform quickly the reactants into products. The use of D orbitals and S orbitals for making temporal bonds through variable oxidation states, because transition metal ions can change their oxidation state, mean they show variable oxidation states. For example, we having here ferric ion. It reacts with iodide. Iodide got oxidized to iodine, and our ferric got reduced to ferrous. Again, ferrous react with S2O8 to negative. It again got oxidized back to ferric, and S2O8 got reduced to sulfate. So this is the way, although we see here there is no change in the iron in final compound. Ferric remains ferric only. Iodide got oxidized to iodine. S2O8 got reduced to sulfate. Probably one among the most important chemical reaction that I like to show you here is the titanium tetrachloride and aluminium alkyl chloride compound. These two make a complex or a catalytic surface for the reaction of formation of polyethylene. The polyethylene that we used as a packaging material, as a product material for all applications. Otherwise, without these catalysts, making these such selective long chains of polymers under normal condition is not possible at all. These polymers are available at throwaway price because of just these catalysts that we are using. So here what happens, this ethene get absorbed here and it occupy one of the position on the titanium in hexagonal site, and one side remains empty for it's just like a chain. What happens in next stage, this ethene will come to absorb this position and moves the chain up. You see here the chain has gone up, position is still empty. Another ethene molecule will come here, attack it, and push the chain up. This is the how this polymerization reaction proceed. Interstitial compounds in D block. Interstitial compounds are formed by small atoms like hydrogen, carbon, nitrogen being trapped inside the crystal lattice of these D or transition metals. This becomes possible only because the voids present in crystal structure of transition metals are having a sufficiently large size to occupy or accommodate these small sized atoms. That's what we see. Here we having a transition metal crystal structure. First possibility is few of the atoms are knocked out, occupied by some other elements. This is known as substitution or alloying. This is a method of alloy formation. Some of the atoms are replaced by some other elements atom. We're getting a substitution compound or alloys. Now, other possibility is small atoms occupy the voids or interstitial spaces. That's why these are called interstitial compounds, because small atoms occupy the interstitial space between the transition elements. Some properties of transition or interstitial compounds. First, they are non-stoichiometric, means the ratio between, let's say, titanium carbide, titanium hydride, the ratio between hydrogen and titanium is not consistent or in the whole numbers. These atoms in voids having fractional numbers like 1.7 you see here, carbide may be 0.95, and their point of view we can say they are neither ionic nor covalent. Their characteristics somewhere lies in between the two. Their melting points are higher than those of the pure metals. This is one application why the interstitial compounds are useful. What happens? Because now when these voids are occupied by the small atoms, they improve the packaging or density as well as the interaction between the atoms. That's why it makes their melting points higher. They are very hard. Some of the boride approach the hardness in terms of diamond. They are close to diamond. Why it is so? Because how the hardness is, hardness means when we try to push it, we push it from here one side, some of the atoms got displaced or some of the layers will get displaced and break out. That breaks these compounds or these elements from solid state. But when we having these interstitial compounds, these voids will act like brakes against the force that's trying to break it. That's why they're having a very hard characteristics. One of the compound like tungsten tetraborate, this tetraboride compound having a 30 gigapascal strength, which is very high. Our atmospheric pressure is only 10⁵ Pascal. So we should say now it is the order of 10⁹ means we are talking about somewhere pressure of 3 lakh atmospheric pressure. Another property is these interstitial compounds retain their metallic conductivity. In many cases, if the composition is right, interstitial compounds show great degree of inertness when they are not reactive. We can say they do not corrode that easily. As the oxidation number of a metal increases, ionic reactivity decreases. This we know very well from Fajan's rule. As the oxidation number increases, the polarizing capacity of our cation increases. That's why covalent character increases or ionic character reduces.